So last Tuesday we defined independence between two events, and then we extended the definition of independence to three events. Now we will make the definition of independence among n events. Okay, so n events, EI, I from 1 to n, are called independent if for a number of indices, say I1, I2, up to IR, in between 1 and n, okay, and this number R is in between 1 and n, right? So for any such that, and the intersection, the probability of the intersection of EI1, EI2, EIR, okay? So this probability is equal to the product of the individual probability. Okay. All right. So you can see if R is equal to 1, then of course there is only one event involved. So the identity must be true, right? Now, if R equal to 2, then for any two of the events EI, then they are pairwise independent. Okay. If R equal to 3, so you select 3 out of the n events, then in the intersections of 3 events has probability equal to the product of the probability of individual events, okay, etc. Okay. All right. So remarks. They are and are from 2 to n non-trivial identity. In the above definition. Okay, so we have so many identities, okay, for n events to be independent. Okay, and you can see that this is equal to 2 to the nth power minus n minus 1. Okay, so it's a huge number because it's exponential with the number of events involved. Okay, questions? Now I would like to introduce a proposition we call proposition 3.4.D. All right, so say that E1, E2, up to En are independent if and only if the probability of B1 intersect B2 intersects up to Bn, okay, is equal to probability of B1 times probability of B2 to the times probability of Bn, okay, where Bi is equal to Ei, our Ei complement for all I from 1 to n. Okay, so that if the event Bi is equal to Ei or Ei complement, and you take the intersections, then the probability of this intersection is equal to the product of the individual probabilities of Bi. And so they are 2 to the nth power identities, right here. Okay. So the proof, all right, is by induction on n. Okay, by induction on n, and even though the technique to prove for this proposition is not difficult, but it's lengthy. I mean, it takes several paragraphs to do so, and so I omitted. Okay, I just say that this can be proved by induction n. Okay. Okay, and so as a supplementary proposition, okay, I will state that the smallest sigma algebra we say G which contains n events E1, E2 up to En is the collection of all possible unions of B1 intersect B2 intersect up to Bn with Bi equal to Ei or Ei complement for all I from 1 to n. Okay, and to illustrate this proposition, because we are a sigma algebra is a logical system that we can do logical operations like not, and or. Okay, and so so that we have closure, right? Right, so take an example. Suppose n equal to 2. Okay. All right, and so let's see. Suppose we have 2. Okay, like here. Right? So this is E1. This is E2. And this is the sample space. Now we want to find the smallest sigma algebra. Alright? Which contain E1 and E2. Okay? So that now, okay, so this part is E1 intersect E2. Right? So this, right, this part is E1 complement intersect E2. This part is E1 intersects E2 complement. Oh, by the way, I has been used this color. So E1 intersects E2 complement. And the last one, the outside, this is E1 complement intersects E2 complement. Okay? Right. And so you can see that E1 intersects E2, E1 intersects E2 complement, E2 complement intersects E1 intersects E2, E1 complement intersects E2 complement. X a partition of the sample space. Okay, right? It's a partition. All right. Now, the smallest sigma algebra G containing E1 and E2, okay, should satisfy 1. S must be in G, okay? But because this is the partition of X, so this is actually it's equal to E2 union okay. All right, so this one must be in G. Second, if E, all right, Now E is a union of E1, E2, E1, I think it's not so clear, but union of events of the type okay. For example, none of these type of events, then that would be the that would be the empty set, right? And only one of this type, then it's just the one of B1 intersect B2, etc. It is possible that you may have 3 of them or 10 of them, etc. It's not necessarily all of the events of this type. Okay, just like here, a union of events from suppose I call this as P. From P, from the partition. Then, okay, then E complement is also a union of events from P, from the partition. Okay, and so the smallest sigma algebra containing E1, E2, and E2 should satisfy that. Okay. Okay, I think it's too rush. I'm sorry. Should have E1 intersect E2, E1 intersects E2 complement, E1 complement intersects E2 and E1. Right? And any possible unions of okay. Of events from P, from the partition. Okay, because if G is a sigma algebra, then and it contains E1 and contains E2, so that should use contain. E1 complement, E2 complement. Okay? Because when E1 is in G, then E1 complement also in G. And when E2 is in G, E2 complement also in G. Okay. Okay. And then we take the intersection. Alright. So E1 intersect E2, E1 intersect E2 complement, and E1 complement, and E2 E1 complement intersect E2, E1 complement intersect E2 complement. Okay, because intersection should be also in the sigma algebra. And then any possible union of events from this Collegis partition. Okay? Right, so any small d sigma algebra should contain this one. Now we claim that G is actually the collection of all possible unions of events from P, from the partition. Okay, now we have to justify, because that for any sigma algebra, if G is the smallest sigma, then they must contain all these things. Okay, so first of all, the first one, the S, as we know, this is E1 intersects E2 union, E1 complement E2, E1 intersect E2 complement union, E1 complement intersects E2 union, E1 complement intersects E2 complement. Okay. Okay, as we show in the Venn diagram. And so from here, right, this one is the union. So S is a union of events from P. Okay, so which is just the union of all four possible events in P. Okay, so this is in G2, of course. Second, if E is a union of events, okay, of events from P. Okay, so then E complement. For example, because we have four pieces, right? And these four pieces are disjoint to each other. And if E is a union, so for example, E is the yellow color union the red color, then the complement of this union is equal to the union of green color and the blue color, right? The reason is because that they form a partition. Right? The other hand, if we have the union of the red color and the green color, right? So if the event E is the union of the red color and the green color, then the complement of this union is the yellow color union the blue color. So it's also a union of two members from the partitions. Okay. So if E is a union of events from P, then the EC is also a union of the rest is the union of the rest events in P. Okay? The rest event P. And so that EC is also in G. Okay? So if E is in G, i.e. So E is a union of events from P. Sorry. Okay. Right. So that is the second point. So we prove that if E is an event in G in this collection, then E complement is also in this collection. Third one. If E1, E2, sorry, I use F2 in G, i.e. each Fi is a union of events in the partition for all I, then the union of I is also a union of events in P, i.e. if I is also in G. Why? Because that the building block will be the intersections, rather. So the building block, we have only 4 building blocks here. Okay? So the union also is a union of event in P, because the building block cannot be divided further. That is the basic building block. So we have that. All right. So this shows that G is a sigma algebra. Okay. Which contains E1. Why? Because E1 is E1 intersects E1 union, E1 intersects E2 complement, and E2 is E1 intersects E2 union, E1 complement intersects E2. Okay. Because E1 is also a union of the 2 of the 4 basic building block, and the E2 is also the union of 2 out of the 4 basic building blocks. Okay, just like here, E2 is the union of the green and the blue color. E1 is the union of the red and the green color. Okay, so now so G any sigma algebra will contain okay, So maybe I will rephrase. I will say any. All right, not just the smallest. Any sigma algebra contain name G. So maybe I say. So any sigma algebra containing E1, E2 should contain all these things. And then we collect only all possible unions, all right, of events from P together, right? And we show that, G is the sigma algebra, contains E1 and E2, all right? So we conclude that G is the smallest sigma algebra containing E1 and E2. Okay, so this example gives you a proof that if we have only two events, then the smallest sigma algebra which contains E1 and E2 will be this collection. Okay. All right, and in the partition P, we have basic building blocks here. So for two events, E1, E2, we have 4 basic building blocks, right? And so when we go back to this proposition, okay, so we go back to this proposition. If we form events of this type, all right, of this type. So the proof of proposition 3.4.E all right. So we let P to be the B1 intersect B2 intersect up to intersect Bn with Bi equal to Ei, our Ei complement for all okay. Right. So if we let P to be the collection of events of this type, okay, then P is a partition of the sample space. Okay? Yes. So it's just like this example. So that is the partition of the sample space. All right? If you want to see it for n equal to 3, okay, so I can here. So the basic so how many basic building blocks do we have? We have 8 basic building blocks. Why? Because we have 2 choices for B1, right? Because B1 can be E1 or E1 complement. B2 can be E2 or E2 complement. Up to here. So the size, and note that the size of this collection is 2 to the nth power. Okay? Okay, and so how many? So the whole subspace can be partitioned into 1, 2, 3, 4, 5, 6, 7, 8 parts, right? If you have 4 events, then you can partition the subspace into 16 parts. Okay? Right. So this type of intersection becomes 2 basic building blocks. Begin to basic building blocks. Okay. All right. Now, any sigma algebra which, okay, any sigma algebra containing E1, E2 up to En must contain B1 intersects B2 intersects up to Bn with Bi equal to Ei or Ei complement for all I from 1 to n. Okay? And any union of events of the type B1, B2, Bn in above. Is that okay? So any sigma algebra containing E1, E2, En must contain any of the event in out of the 8 pieces. Okay, so because each piece is of the type here. For example, number 1 is E1 intersect E2 intersect E3, right? So it's the intersection of EIs. Okay, and the outside is the intersection of the EI complement or EI complement. Okay. For example, all right, so is that okay? Okay. All right, and so now we let G to be the collection of all possible unions of events in P. All right, in this partition. Okay. And then we show, then first, the total event is just the union of the events in P. Okay, it's the total union. So it's also in G. Because it's the partition, so the union of all the events in the partition should be the total event. If E is in G, i.e. E is the union of F in the Q, where Q is a sub-collection of P. Okay? So Q is a sub-collection means that because P, for example, P consists of 8 members, and any sub-collection just part of just a collection of some of the members together. Okay? Right? Then E complement. Then E complement becomes to the union of F in the P minus Q. Okay? And of course, so it's a union of events in P. So that E complement is also in the G here. Okay? So for example, if F, if the event, if E is the union of, for example, 5, 6, 7, okay, union of 5, 6, 7, then the complement of this union will be the union of 1, 2, 3, 4, and 8. So it's very simple, right? You can see from the Venn diagram. Okay, so the second one, so if you take the nut, you have third one. If E1, if G1, G2, up to G, etc. In G, i.e., each GI is the union of F in QI, where QI is a subcollection of P for all I. Alright, then the union of I of GI is also the union of QI. Okay. And it's also a union of events in P. Because each QI is a subcollection, so the union of subcollection is also a subcollection of P. Okay. So that is in G too. Okay. So from 1 to 3, sigma algebra. Okay. Right. So G. The sigma algebra, and which contains EI. Why? Because that EI is the union of B1 intersects B2 intersects BI minus 1 intersects EI intersects BI plus 1 Bn. So maybe So you take Bj is equal to EC over Bj is EJ over EJ complement for all j not equal to I. Okay, so basically it's the union, disjoint union of the basic building block. Okay, and the basic building here is that in the ith position we have EIs here, but the other position will be BI, BJs, okay, and the BJ can be EI, EJ or EJ complement. Okay, so this is the union. Okay, and of course that it is a union of events in the partition when we express that. Okay, so for example, this one, suppose this is E1, it's E1 intersect E2 intersect E3. Union E1 intersects E2 intersect E3 complement. Union E1 intersects E2 complement intersect E3. Union E1 intersects E2 complement and E3 complement. Okay. Okay, so you have 4. 1, 2, 3, 4. Okay. So in here, they are 2 to the n-1 terms here to get EI. Okay, because when we have 2 to the nth power building blocks, right? Basic building blocks, and to get EI, we should take the union of 2 to the n-1 basic building blocks. Okay, UK 2 minus 1 terms are basic. All right, maybe that would be better. Alright, so G will show that G is a sigma algebra contain EI, and G is just collection of all possible union of events in P. But in here, we have shown that any sigma algebra contain any union of events of the basic building block. Right. So the conclusion. So G is the smallest sigma algebra containing E1, E2 up to En. End of the proof. Okay. All right. So we just prove this proposition. Okay. And a remark. So remark. Okay. This smallest sigma algebra G will be containing E1, E2 up to En, will be called the signal algebra generated by the collection E1, E2 up to En, and will be denoted as G of E1 okay. One second. The size of the partition P in the above proof it's 2 to the nth power. Okay, so that's the size of G okay, will be less than or equal to 2 to the, so this is 2 to the 2 to the nth power. Okay. And most often we have equality. The reason why I put the less than or equal to this one is because maybe some of the members in P alright. In this collection, we have 2 to the nth powers, right? But some of the members may be empty set. Why? Why? Well, for example, suppose we have this situation. Okay, and so that in this situation, the E1 intersect E2 intersect E3 is the empty set. Okay, and this is E1, so this is E2, this is E3, and okay. And also E1 intersects E2 complement intersects E3 is also empty set. So we have 2 empty sets there. Okay? And so if you take union with an empty set just does not change the result. So this is the reason why maybe the size of the smallest signal algebra G may be less than the 2 to the size of P. Because when you select the union here, the select unions, you can take any basic building block may be put into the union or not. So you have 2 choices. The reason, so that is the reason why the size is basically is this one. So if the partition P contains non-empty sets, so if the 2 to the nth power basic building blocks are all non-empty, then we have equality sign. So, and equality holds if and only if P contains no empty sets. Empty, maybe I say empty members. Okay? Right? So when P contains no empty members, then the size of the signal algebra will be equal to 2 to the 2nth power. Okay? So that is a huge number. Okay? It's a huge number. If n is big, okay? For example, when n is 10, 2 to the 10th power is 1,000. And so you have 2 to the 1,000 power. Okay? And 2 to the 1,000 power is 10 to the 300th power. Okay, that is a huge number already. Okay? Okay, and the third one, G of E1 contains all events concerning relating to I will use the word formed by events E1, E2, and En from events by logical operators, by maybe I'll say countable many logical operators. Okay. Not and or. Okay, you can repeat it to not and or, something like that. Okay. And so you can see it's a huge number. Okay. If you have n events, these n events can induce lots of events, right, from these n events. And how many of them? At most will be 2 to the 2 to the nth power. And as I just showed you, it's a huge number. Even n is just 10 events. Okay? If n is 5 events, then this is 32, right? So 2 to the 32 power would be about 1 billion, right? About 10 to the 9th power, so 1 billion. Okay, so 5 events after logical operations will give you 1 billion possible different events. That's a huge number, all right? So the complexity is big. It is very big. Any questions? Okay, so then let's take a break of 5 minutes.
就这边推的时候是怎么推出它是 smallest？
Okay, right. Now, we will apply the last proposition. I just erased that. Proposition 3.4.e to state the following property. Okay, so if E1, E2 up to En are independent. So now we go back to our study of independence. Then each EI will be, each EJ, I use J. Each EJ will be independent of any event formed from EI I not equal to J by countably many logical operations or operators. Okay, I state this when we consider the n equal to 3, right? So I say, but this is generally true. So if n events are independent, all right, then EIs will be independent of any events of that. Okay. All right. So I'll give a proof. Okay, now give a proof of that. Okay, so let G be EI but be the sigma algebra, okay, generated by EIs for I not equal to J. Okay? Right? As we say, this sigma algebra contains all possible events formed from EIs I not equal to J. Okay? So it's a huge amount of events here. So this is there. Okay, so by proposition, all right? So by proposition 3.4.e, all right? F in this sigma algebra okay, if and only if F is equal to the disjoint union of B intersection of BI right? And so here, so maybe I will use B1 Bj plus 1 Bj plus 1 Bn. Okay. Okay. Union of events of type okay, maybe I will say that. Is that okay? Then probability of EI, because I want to show that EI intersect F. Now I want to show that EJ, I'm sorry, EJ is independent of F. Okay? So this would be the probability of EJ intersect a union of events of type B1 intersect Bj minus 1 intersect Bj plus 1 intersect Bn. Okay? Now, by the distributive law, because this is the intersect to union, so this is probability of a union right? A union of EJ intersect events of type B1 Bn. Okay, and so that this is actually equal to probability of a union of the type of events of the type B1 intersect Bj minus 1 intersects EJ intersects Bj plus 1 intersects Bn. Now, any questions? And this one must be a disjoint union, right? Why? Because they are in a partition of the sample space. So they're disjoint union. And so this is disjoint union. and this is a disjoint union. Okay. Now, by the countable additivity of probability function, so this is a sum of probability of events a sum of B1 Bj minus 1 okay. The type okay, because we have the joint union. Now a sum of P B1 P Bj minus 1 P Ej P Bj plus 1 P okay, by proposition 3.4.d, because E1, E2 to En are independent. Okay, so that the probability of events of this type is equal to the product of probability of individual events. That is proposition 3.4.d. Okay, and so this becomes to probability of Ej times a sum of P B1 P Bj minus 1 P Bj plus 1 P Bn of events of the type B1 Bj minus 1 Bj plus 1 Bn. Alright, and so this is Pej. So times a sum of P B1 intersects up to Bj minus 1 since independence of implies independence the definition of independence. Okay. So you look at, if we have n event which are statistically independent, then any subcollection of this n event should be independent too. Right? So the independence of n events implies independence of n minus 1 events. Okay. So that again, by applying and by proposition again, proposition 3.4.d again, but this time we apply to n minus 1 event. And this is the probability of Ej times probability of union of events of the type B1 intersects Bj minus 1 intersects Bj plus 1. Okay. And this is probability of Ej times probability of F. And we have done. Okay? Complete proof. Because the union here is F, right? That is a union of events. So we prove that the probability of the intersection of Ej and F is equal to the product of probability of Ej and probability of F. We prove that. Alright, and so we prove this statement. So if E1, E2, and En are independent, then Ej will be independent of any event from all Ei not equal to J. And so for the proof, you can see that if we change Ej to Ej complement, the statement is also true. Right? So if E1, E2, and En are independent, then Ej complement will be independent of any event formed from all Ei not equal to J by countably many logical operators. Okay, so this statement tells us that independence among n events contain a lot of information. A lot of information, truly. Okay, that Ei, Ej will be independent of the event formed from all other events. Okay. Any questions? And this statement can be extended again. If Ei are independent, then any event formed by a number of EIs from EI1, EI2, EIR, okay, by countably many logical operators. Right? So from n events, we select some of them. Say R of them, right? R of them. R can be 1 up to n minus 1. Okay? R of them. Alright? And from this R events, we form an event by taking not n or in any order, right? Okay, so we can form that. Then any event is independent of any event formed from the raised events EI not equal to I1 many logical operators. Okay? So you can divide the n event into two groups. Okay? Into two groups. And you use one group to form an event by counting many logical operators. And you use another group to form another event by counting many logical operators. Right? So you have one event from this group, another event from this group. Then these two events must be independent. Alright? And specifically, we have proposition 3.41f. So let E1, E2 up to En be independent events. Okay? Let J and K be then for any E in the sigma edge in I1 for Okay? For any event in the sigma algebra generated by EI1, EI2, and EIR, and any f in G, EI, right? And f is an event in the sigma algebra generated by the waste events EI. Okay, so for any E and F, we have E and F are independent. Okay. So independence, the definition of independence, as we, for n events in today's lecture, at the beginning of today's lecture, is that we use 2 to the nth power minus n minus 1 identity to specify it, right? Okay. And this concept actually give us a lot of consequence, a lot of results, and one of them is this one, right? So you can divide this n independent event into 2 groups. Okay. If you like to divide it into 3 groups, that's fine. You will have the similar result if you like, because the proof will be the same as this one. So if you know you understand the proof here, then you can extend the result to different situations. Okay, so if you have an event and you divide it into, for example, 4 groups, and each group generates an event, so you have 4 events, then these 4 events will be independent of each other. Okay? They will independent of each other. Any questions? Okay, now, how about we have an infinite collection of events? It's called independent. Okay, so suppose we have E1, E2, E3, etc. So we have countably many, even uncountably many events. Okay, so an infinite collection of events is called independent. If every finite subcollection of those events is independent. Okay, so if you have a collection of infinite many events, and we say this collection of events is independent, if you pick up arbitrary finite subsections, okay, and this finite subsection must be statistically independent. Okay. So that this is the way to define independence for an infinite collection of events. Okay? All right? Now we will build a model, and in some random experiments, we do a sequence of trials. For example, a trial possibly to toss a coin. Okay, toss a coin once. That is one trial. Second time, the second trial is that. So you may perform tossing a coin for even many times. Okay, so we have. Okay, and so how do we build a probability space or a probabilistic model for a sequence, means an infinite sequence of trials, like tossing a coin? Okay. Here is the description. So I will say sometimes a random experiment under consideration consists of performing a sequence of we call sub-experiment. Okay? Thanks. Right? And sub-experiment are called independent if the outcomes of any group of sub-experiment have no effect on the outcomes, right, on the outcomes of other experiment of the other sub-experiment. Okay. All right. So if you perform tossing a coin, that is a trial. You do it the second time, that is the second trial. And usually, the trial to tossing a coin can be think about as independent, has no effect of the next trial. Okay, right, and etc. Okay, so these sub-experiments are called independent. So formally, to describe independent experiment, sub-experiment, we will say, so formally, if E sub n is an event whose outcome, whose outcomes, or we just say whose occurrence, whose occurrence is completely determined by the outcome of the nth sub-experiment. For n from 1 to etc. Okay, so E1 is an event whose occurrence is completely determined by the outcome of the first experiment. E2 depends on the outcome of the second sub-experiment, etc. Right? Then we will regard this infinite collection of events, is a set. It is a set of independent events. Alright, so in this situation, we will consider an infinite collection of events. And this collection is independent. And the reason is that there are many situations sub-experiment may be regarded as independent. Alright, if each sub-experiment has the same set of possible outcomes, then the sub-experiments are often called a trial. Okay, so we will establish a probabilistic model XFP for a sequence of independent trial. All right. Okay, so our sub-experiments are experiments that they have the same set of possible outcomes. So basically, they do the same sub-experiment. For example, tossing a coin, throw a dice. Okay. So there are many different sub-experiments, and we will assume that different trials have no effect with other trials. So we have independent trials specified here. So if if En is an event, okay, whose occurrence completely determined by the outcome of the nth trial, right? So now E1, E2, etc. This sequence of events will be independent of each other. And by our definition here, for such independent infinite collection of events, it says that if we take out a finite subcollection of events, then they are independent of each other. Okay. Okay. All right. So first of all, we let A, B, and P0 be the probabilistic model of a trial. Right? Right, and A is the set of all possible outcomes of a trial. And B is a sigma algebra of subset of A. Okay, for example, when a trial exposing a fair coin, then A is H head and tail. Okay, so there are only two possible outcomes. Right? And the sigma algebra would be 2 to the power set of A, so that it would be empty set, the atomic event, H and T, and the A itself. So there are 4 events of interest. Okay, this is an example for that. And P is a probability function and the P0 is probability function on the sigma algebra B. For example, when a trial exposing a coin the probability function P0 can be the counting probability measure means that P0 of the atomic event will be 1/2. Okay. Okay. So first of all, we should have a probability model for a trial. Okay, that would be simple because a sub-experiment or usually simple random experiment. All right, so the probability space or the probabilistic model A, B, and P0 would be very simple. Okay, so now we will establish a probabilistic model for a sequence of independent trial. All right, so on Tuesday, remember we will have a pre-makeup lecture on the coming Saturday, March 5th in the afternoon. So I will continue to specify how to build such a probabilistic model from the space, okay, from the probabilistic model of a trial, okay, so that in the future we are able to study, to investigate a sequence of independent trial, okay. All right, so I'll stop here and I'll see you on Saturday.